So this is a GeoGebra view of the solution to the orbital equation. If you look over here, this is sort of the general form of the orbital equation, b over 1 plus a cosine theta minus theta naught. Now, the b is really ml squared over k, as in the notes, and the a has the ml squared over k constant built into it, but it also has a coefficient which we actually called a in our notes, and it's got this initial angle. And so I'm just going to show you what the solutions look like graphically to this equation for various values of what I've used here as a, b, and theta naught. And so if I set a equal to 0, which is right about, here, this becomes a perfect circle. This is the equation for the radial position, right? And if a is 0, then the radius is just b, right? Independent of theta. And so you can see that if I scale b up and down, if b is 2, then the radius is 2. If b is larger, then the radius is larger, and so on, right? And similarly, if I go the other way, it's a little weird if I make it negative, but really I'm just talking about the magnitude of this. And so I get circles for the case where a equals 0. And so now let's pick a value of a that's like something different from 0. And notice here's where I start getting an ellipse, right? And so the more I make a close to 1, the more elliptical I get. If a gets to 1, the orbit is actually parabolic. And I'm going to show that by shrinking b back down. So I'm just going to scale the whole thing down a little bit. And now let's look at what happens when I increase a, and you can see, so right about there, when a equals 1, this thing becomes parabolic. Like I said, b just scales it down. So let me just go back to an elliptical orbit. So a parabolic orbit is also a solution for this, not just ellipses and circles. And you can kind of see, here's an ellipse again. And so you can see the center here is one of the foci, right? I'll make it a little bigger. And now let's vary theta naught, right? What theta naught does, let me get rid of that. What theta naught does is just change the orientation angle. And so usually we're not that interested in that. We don't care what the initial angle is. We just care that what the shape of the orbit is. And so usually you'll see in most of the problems we do, theta naught is just set to 0. It doesn't really matter. It's just you can have any orientation for that orbit. And so now let me go back to the a. So I said when a gets up to 1, the orbit is parabolic. And then beyond that, it's a hyperbolic orbit. And so you can kind of see as I get to larger and larger values of a, the orbit becomes a hyperbola. And so all of these things, hyperbolas, parabolas, ellipses, and circles, are all legit orbits for the solution to a central force that goes as 1 over r squared. And these are called conic sections. And these are what Newton discovered would be all the allowable orbits for objects in orbits if the gravitational force goes as 1 over r squared. So this is just going to be a short discussion on an ellipse where we're going to define some terms. An ellipse is the locus of points, the sum of whose distance from two fixed points is a constant. And so if you look down here, there's a focus here on the left, and there's a focus here on the right. And what the ellipse is, if you imagine you had a loop of string that went around both foci, and then you stretched it tight over to where r and r prime meet on the right, and held it tight with a pencil, and then just stretched that pencil out and followed all the way around the loop. Whoops, I made a little line there, I wasn't trying to. All the way around and back, that loop would trace out an ellipse, because the loop that went around the two foci, one side of it would be held completely straight, taut, and the other two would be stretched to the point of the ellipse. And so the sum of the other two lines, in this case r and r prime, would be constant. They would be constant up here at point C. They would be constant on the axis, on the major axis of the ellipse, and at every other point. And so a plus a, the red lines, have to add up to the same number as r prime and r, because that's how ellipses are defined. And so there are a couple other things you can say. I call this a, and actually a is the semi-major axis of this ellipse. So the semi-major axis is half of the major axis, so it's the distance from the center to the long edge, and that's a. And it turns out it's also this a, and I'll tell you why. Because when we have the string stretched all the way out here to the left, right, that means the loop goes to this focus point and then all the way around here, as it always does between the two, and then it comes all the way back. And so if I take the length that went from this edge to this focal point and stretched it across here, then the extra length would add up to the full semi-major axis. And so the full semi-major axis is how long r and r prime are. Or in other words, r plus r prime is just 2a. Well, this also has to be 2a because r and r prime have to add up to 2a everywhere. And so since they're symmetric here, each one of these lengths is a. And so that's a semi-major axis, and that's a semi-major axis. It's from the foci to the symmetry point. Okay, there are a couple other things we want to talk about. First of all, the minor axis here is we're calling b, right? And this angle theta, which is the one that appears in our equations, is the angle between where you're measuring from and your r. And so when we, in our example earlier, we had something like b over 1 plus a cosine theta. This is the theta that we're talking about. This distance here from the center to the focus is epsilon times a, where epsilon is called the eccentricity of the ellipse. If epsilon is 0, the ellipse is a circle. Both points meet in the center if epsilon is 0. And so for an ellipse with 0 eccentricity, I get a circle. If epsilon is 1, that is to say the distance from the center to the focal point is the same thing as the semi-major axis. That means the focal point is at the edge of the circle, and that means that it's a straight line. And so the two extremes for an ellipse is a circle where the eccentricity is 0 and a straight line where the eccentricity is 1. And in between you get all these different types of ovals. Finally, R1 here is called the apocenter. It's the distance from the focus, which is at your origin, to the long edge along the major axis. And the pericenter, these sounds like apohelion and perihelion, and R0 is called the pericenter. And so the apocenter and the pericenter. So this is the last piece of this discussion about ellipses that comes up in our study is understanding this piece, which is called the latus rectum. It's the vertical line. Vertical is in perpendicular to the semi-major axis from one of the foci to the ellipse, right? And so it's a perpendicular line to the major axis, and from a focus to the point where it meets the ellipse. And we can make a right triangle by including this blue line, whose length is 2a minus alpha. Again, the latus rectum's length is alpha, and so the blue line has to be 2a minus alpha because they're connected to 2 points on the ellipse from the foci, and that means they have to add up to 2a, and so this has to be 2a minus alpha. And then the line connecting the two foci is 2 times the eccentricity times a, or 2 epsilon a. And so we can do a Pythagorean theorem to learn what the value of the latus rectum is. It's 2a minus alpha quantity squared minus 2 epsilon a quantity squared equals alpha squared. And if you just expand these guys out and do just a little bit of algebra with them, you get the latus rectum is equal to 1 minus epsilon squared times a. And again, epsilon's value is somewhere between 0 and 1, and so this quantity in parentheses is somewhere between 0 and 1 times a, which makes sense. The maximum, if alpha can be equal to the radius if it's a circle, and anything less than that, it's going to be smaller than the semi-major axis. So this number makes sense. So our last little thought about ellipses, well, maybe not our last, but some concluding thoughts are that this is our general formula for ellipses, and this was the general formula that we sort of arrived at the end of our differential equation solution for the orbit. And so if you compare these two, you can say, well, the ml squared over k gives you the lattice rectum of the ellipse, right? The eccentricity is given by the coefficient of cosine theta, which for us was our constant, which we'll get from the initial conditions of the differential equation, times ml squared again over k. And so if you know the form of your force, you can determine the orbit. And we can look at interesting parameters for an orbit. We'll talk about, like for the sun's orbit, we'll talk about perihelion and aphelion, or for objects that are orbiting the Earth, we'll call perigee and apogee. And that's what these two quantities, R1 and R2, are from our diagrams, and I've just sort of sketched them here. And if you notice, this is this distance is the semi-major axis, and so that's A. And so the epicenter, the pericenter, is just A minus epsilon A, which is what I've written here, and that's just A times 1 minus epsilon, which is just the lattice rectum over 1 plus epsilon, because if you remember, the lattice rectum alpha is just A times 1 minus epsilon squared. And so that's just the same thing as 1 plus epsilon times 1 minus epsilon. So if you divide it by 1 plus epsilon, you get A times 1 minus epsilon. Similarly, the apocenter is A plus, it's this distance plus this, so it's A plus epsilon A, and it's the same thing as A times 1 plus epsilon, which is lattice rectum over 1 minus the eccentricity. And so finally, and this we talked a little bit about when in the GeoGebra example, when the eccentricity is 0, you get a circle. When the eccentricity is less than 1, you get an ellipse. A circle is a special case of an ellipse. When an eccentricity is equal to 1, you get a parabola, and greater than 1, you get a hyperbola. And those are all the conic sections. That comprise all the possible orbits in a 1 over r squared force. We'll follow this with some examples.